Hello everyone, rigid body mechanics again. This part is about constant angular acceleration. Of course, equations of motion. Let's learn them from scratch. Consider an object here moving in a circle at this point t equals 0. It has an initial omega of omega I, initial angular speed. Through a displacement of theta, angular displacement of theta, it goes to another omega like omega final at the time t. Let's say change in omega has a constant rate, means that delta omega over delta t is constant. And you know that delta omega over delta t is called angular acceleration. So omega versus t will have a linear increase or maybe linear decrease. So it has a linear behavior. It could start from omega I linearly increases to at the time t to something like omega final. The slope of this graph indicates change in omega in every second, means it's exactly delta omega over delta t. That's called angular acceleration. It must be constant. So slope of omega t graph here is constant, and also it's supposed to be angular acceleration. So let's write it as omega final minus omega initial divided by t. Let's have a change in this equation and make a cross product and find it as omega final equals alpha t plus omega initial. It's very similar to v is equal to at plus u in linear motion. This is initial velocity, this is final velocity, and this is acceleration. Similarity is clear. Okay, let's continue with that. Do you remember in linear motion I told you the area under the vt graph indicates displacement. So by similarity, area under the omega t graph will indicate angular displacement. So it must be theta. Okay, now let's find the theta. Here we have a trapezoid. You see, it has a large base of omega final, small base of omega initial, and the height of t. So let's write omega theta like that. Large base omega final plus small base omega initial divided by 2 times height. That's all. So this is the theta, angular displacement. Moreover, you can import omega final to this equation. How? Look, theta is omega final plus omega initial times t divided by 2. But omega final is also omega initial plus alpha t. If we do that, we have this equation. So theta is supposed to be alpha t plus 2 omega initial divided by 2 times t. And if we rearrange this equation, I will have theta equals a half of alpha t square plus omega initial times t. It's very similar to x equals a half of at square plus ut in linear motion. Very similar. Finally, we can invent and extract the last equation time independent. How? It's very easy. Look at this. Here alpha is omega final minus omega initial divided by t. So let's say t is omega final minus omega initial divided by alpha. And let's plug in this equation here. So theta is supposed to be omega final plus omega initial divided by 2, and it's times omega final minus omega initial divided by alpha. That's all. On top, you see conjugate identity. And so it's supposed to be omega final square minus omega initial square divided by 2 alpha. That's all. So we can write it in this form. Omega final square is equal to omega initial square plus 2 alpha theta. It's very similar to the equation, similar equation we had for time independence in linear motion. V square is equal to u square plus 2ax or delta x. So let's make that similarity in this table. In linear motion, we had v equals at plus u. Now we have omega equals alpha t plus omega initial. The other is x equals v plus u divided by 2. Final speed, initial speed divided by 2. Now we have omega final plus omega initial divided by 2 times t. Very similar. And this x now is substituted for theta, angular displacement. x equals a half of at squared plus ut. X here would be theta. A will be alpha in rotational motion, and u, initial velocity, will be omega, initial angular velocity. And finally, as I mentioned, time independent equation v squared is equal to u squared plus 2ax. Similar to that, omega squared, omega initial squared plus 2 alpha theta. Very easy to learn, but basically whatever we can extract always for this motion is based on the omega t graph that has a linear behavior. Of course, line may be ascending, may be descending, depending on the type of motion, but it has a constant slope, and the slope is alpha. And the area under the graph, as I mentioned, is always change in theta. I mean delta theta, or simply we can say angular displacement. Okay, let's go over this equation. The graph shows how the angular velocity of a rotating cylinder varies with time. Calculate part A, the angular acceleration of the cylinder during the first 4 seconds. Look, during the first 4 seconds, I see a linear increase. So it has a constant slope. Then angular velocity, the omega, goes to a constant value and continues forever. No acceleration anymore. So at the beginning it has acceleration. This acceleration is supposed to be the slope of this graph. To make the slope, we can establish a triangle, a right triangle. Vertical divided by horizontal will be the angular acceleration. So vertical is 5 and the horizontal is 4. So the slope angular acceleration is 5 over 4. Done. Part B. The angular displacement of the cylinder from 0 to 10 seconds. In whole motion, we are looking for the total theta, angular displacement. As I mentioned, the angular displacement is the area under the graph. We have a trapezoid. The large base of this trapezoid is 10, the small base seems to be 6, and the vertical, the height is 5. So it's supposed to be 6 plus 10 times height divided by 2. And easily it will become 40 radians. 40 radians is the total angular displacement, all in 10 seconds. Next question. The angular acceleration of a wheel rotated from rest means omega initial is 0, is 16 radian per second square. Okay, the wheel accelerates for 5 seconds. Calculate part A, final angular velocity. Instead of using equations, I directly use omega t graph. It's very easy because all equations were extracted from omega t graph. It starts from rest, means that it starts from here 0, and then increases to 16 radian per increases to something with a rate of 16 radian per second square in 5 seconds. Means that the slope of this graph, rate of change of omega, is 16 radian per second square. Means that in each second, the increase in omega will be 16 each second. If it continues for 5 seconds, it will have a change 5 seconds. It will have a change of 16 times 5 times of 16. So the final omega, easily according to the slope, will be 80. So it goes to maximum omega of 80 radians per second. Very easy. No need to use any equation. Part B, the number of revolutions of the wheel in reaching this angular velocity. What do they mean by number of revolutions? Guys, you know 2 pi is a complete revolution. One full cycle is 2 pi. So if I know, for example, that theta is 4 pi, it will be 2 revolutions. And if it is 6 pi, it will be 3, easily. So you divide the theta by 2 pi and find the number of revolutions. First, I need theta. How to find the theta, the total angular displacement? Easily, the area under the graph. That's all. Area under the graph will be the area of this right triangle. Vertical side is 80 and horizontal side is 5, so it's 80 times 5 divided by 2. So easily it's 200. 200 radians. Then I divide it by 2 pi because each 2 pi is a complete revolution. It's almost 32 thirds. This is the answer. Done. Let's go to the next question. Spinning top. Spinning top is an object when you start rotating that. At the beginning, it has maximum number of rotations, maximum omega per second. And then after a few moments, due to the friction, it will lose energy and may drop. Okay, let's read the question. A spinning top is rotating with an initial angular velocity of 30. So maximum omega at the beginning is 30. Due to friction, as I mentioned, it will reduce to some smaller value. It decelerates at a constant rate of 0.45. Decelerates means that change in omega in every second will be negative 0.45. Change of omega in every second. This is called angular acceleration. A negative sign is because of deceleration. Okay? The top falls over when its angular velocity has decelerated to 5. So minimum number of rotations per second will be 5. After that, not number of rotations, sorry, the minimum omega, it will be 5 radians per second. And after that, it will fall. So it could be the minimum omega possible for having this spinning top in vertical position. So let's say the omega starts from here, 30, and decelerates to the minimum value of 5 at a rate of negative 0.45, the slope. Okay, part A. The time it takes for the top to fall over. The time. Here we are looking for this time, t. How to find it? It's very easy. Just think about the concept of a slope. Slope here means the rate of change of omega. I establish a triangle. I see the delta omega here, and I will have delta t here. Delta omega over delta t is supposed to be negative 0.45. And of course, delta omega you see is supposed to be final omega minus initial omega, so it's negative 25. So it will be negative 25. And done. We can easily find the time, 56 seconds. Part B. The number of rotations the top makes before it falls over. Number of rotations, again, will be the total angular displacement, as I mentioned, divided by 2 pi. Because each 2 pi is complete revolution. So maybe 10 pi divided by 2 pi will give you 5 revolutions. Anyway, I don't know how many revolutions it may have. So at the beginning, I start finding the theta. Theta will be the total area under the graph in whole 56 seconds. I have a trapezoid. Larger base is 30, small base is 5, and height is 56. So theta is supposed to be 30 plus 5 divided by 2 times the height 56. So 970 is the total angular displacement, theta. Then I divide it by 2 pi, as I mentioned, and it's supposed to be almost 150. This is the number of turns, number of revolutions from 30 to 5, omega 30 to omega 5. Then it falls over. Okay, next question. A merry-go-round of radius 2 meters is rotated from rest. So let's say we have a merry-go-round like this, a disk of a radius of 2, and it starts from rest, okay, with a constant angular acceleration, and makes 2 complete revolutions during a time of 16 seconds. So 1 complete revolution is supposed to be 2 pi. Means that for 2 complete revolutions, I expect 4 pi. So the total theta, the angular displacement, seems to be 4 pi in 16 seconds. Okay, part A, angular acceleration. Good. Let's again start from the scratch. The graph of omega t. How? It's very easy. Omega starts from, because it starts from rest, starts from 0, and it will raise up to something, and then the total time is 16 seconds, okay? We are looking for angular acceleration, the slope. Look at this triangle. The slope is vertical divided by horizontal. I know the horizontal side is 16, but I don't know the vertical side. How to find the vertical side? It's very easy. I can find the total area under the graph, and then this area will lead to the vertical side. Okay? What's the area under the graph? Through the number of revolutions, it's very easy. I mentioned 2 revolutions means 4 pi of theta. So the total angular displacement is 4 pi. Means that 4 pi, the area of this is supposed to be height. Let's say the height is omega times base, which is 16 divided by 2. Done. So final omega will be pi over 2. Okay. Then a slope is vertical divided by horizontal. Very easy. Pi over 2 divided by 16. So it's pi over 32. The first part is done, alpha. I will take all the data I found and given to the next part, part B. This is the graph we needed. The final linear speed of a point on the circumference of the merry-go-round. On the circumference means that the radius is 2 meters. Okay, what's the goal of this question? Final linear speed. You remember, from rotational to the linear motion, we had an elevator. If I know the omega, I can multiply by r and find v is equal to r omega, according to the map I developed. So final velocity will be final omega times r. Easy. Final omega is pi over 2, and the radius is given to be 2 meters. So the answer will be 2 times pi over 32, which is pi over 16 meter per second. Final linear speed. Okay, part C. The time it took to complete the first revolution. Guys, first revolution means that it goes through one complete circle. It is 2 pi. So the area under the graph, as you remember, was 4 pi in 16 seconds. I don't know how many seconds it takes to have just 2 pi change. So let's say there is a target time like t, and the total angular displacement through that time interval will be 2 pi. It must be one complete revolution. Okay, I'm looking for this t. I have a triangle. The area of this triangle is a noun value. I know this is 2 pi. And I'm looking for the horizontal side, the base. Okay, it's very easy. You know that alpha is the slope of this graph. Okay, so alpha is supposed to be vertical divided by horizontal. Let's say horizontal is t. Okay, vertical is omega. There is a value of omega like this, and omega divided by t, vertical divided by horizontal, is supposed to be pi over 32, the slope. So omega seems to be pi over 32 times t. This is the omega I expect after t seconds according to the value of the slope. Again, vertical is omega, horizontal is t. Omega divided by t is supposed to be a slope, pi over 32. So omega is pi over 32 times t. Now I complete the task using the concept of area. The total area under the graph is 2 pi. Horizontal is t. Vertical is pi over 32 times t. Okay, divided by 2. It's supposed to be 2 pi. That's all. So I can just change the equation like that. T squared is 128 and t is supposed to be 11.3 seconds. It's the time you need to have one complete revolution. I mean the angular displacement of 2 pi. You see, omega t graph can solve all questions. A diagram shows a hula hoop, a large plastic ring. You know what's that? rolling with constant angular speed along a horizontal surface. This is the horizontal surface, okay? A. It then rolls down a uniform inclined plane, comes down through rolls down the slope of B. When it reaches the second horizontal surface C here, it moves with a constant angular speed. Okay, so I have a constant omega here, omega a constant omega here, omega c, and variable omega through the ramp, because on the ramp, the object will have acceleration anymore. Anyway, okay, sketch and explain the graphs to show the variation with time of angular velocity and angular acceleration. Okay, so I need omega t graph and also alpha t graph. Let's do it. It's very easy. Here we have a constant omega, so omega won't change. And then omega increases at a constant rate because acceleration, and so linear acceleration on the ramp will be constant. You remember I told you I have alpha in the circle, and on the circle I have tangential acceleration, okay? Alpha is supposed to be multiplied by r to give you at. So tangential acceleration is radius times alpha, according to the map. Here, radius of the hoop is constant. So if we have constant acceleration on the ramp, we have constant angular acceleration on the ramp. So angular acceleration will be constant, omega will raise, the slope is constant to something larger. And then again constant on the horizontal part C. So alpha on A will be 0, no alpha because there is no force acting on the object, no acceleration. Then constant alpha, the part B, and finally again 0 alpha in the part C. That's all. This is a qualitative graph for omega t and alpha t for this hoop. Thank you for your attention. Thank you for being with me. I hope you enjoyed this video. See you soon.